Hi guys, Shouvik here. Welcome back to our YouTube channel. So today we are back with another banger questions, I have to say. So let's get started. Yeah. So for today we have this question, that is minimum cost walk in weighted graph. So let's read out the question. That is quite high statements we have to read out. So let's do. So so in the questions they have given an undirected weighted graph with n vertices, labels from 0 to n minus 1. So there are n vertices graph is given to us, which is labeled from 0 to n minus 1. Right now you are given an integer n and an array ages, where ages I represents ui vi wi. So that is very standard representations of a graph. So that means from ui to vi there is a bidirectional edge of weight w, indicates there is an edge between vertices u and v with weight w. Now a walk on a graph is a sequence of vertices. A walk on a graph is a sequence of vertices and edges. The walk starts and ends with a vertex. Now there is a definitions they are providing of a walk. Now how they are basically defining a walk. So a walk should start from a particular start and end with a end in a particular end vertex with the end vertex, and each edge connected the vertex that comes before it and the vertex that comes after it. And it is important to note that a walk may visit some edge or a vertex more than once. So if I consider if you have to walk from index 0 to 3, you can go to from index 0 to 1, 1 to 3, or you can go to from 0 to 1, 1 to 2, and then again back to 2 to 1, and then from 1 you can again back to 0, or you can go to 3. So you can do like walking to same path, same node multiple times, same edges, same node multiple times. So that is the beauty of this particular question. So you can do like redundant visiting of a particular node, redundant visiting of a particular edges. You can do so. Now the cost of a walk from a starting node u and ending at a node v is defined as the bitwise end of the edges traversed during the walk. Now what is the cost if you start from node u, and if you are end at node v, is defined as the bitwise end. You have to do the bitwise end of all the weight you have visited till your walk, and we have just defined our walk. And in other words, if the sequence of edge weights encountered during the walk are w0, w1, w2, like this wk, the cost is calculated at w0 to bitwise end till wk, where and is the bitwise end operator. As simple as that. Now you are also given a 2D array query, where queries I basically providing on every query there is a start node and the end node is given to you, and for each query you need to find the minimum cost of walking, minimum cost of the walk starting from si and ending at ti. As simple they are expecting. So they have given you the graph, they have given you the graph with the weights, and now they are throwing you the query. You have to tell them starting from node si ending at node ti, what is the minimum walk value you can calculate, and what is the walk you can visit a particular edge or particular node multiple times, and you have to provide the minimum of them. How we are calculating a particular value to a walk, that is the bitwise end of all the weight we have visited so far, If there exists no such walk altogether, like if we are not able from start vertex we are not able to reach the end vertex, then on that case you can return a -1 for this particular query, right? And now return the array answer, where answer I denotes the minimum cost of the walk for the query I, right? So that we have to return. I think question is very straightforward, but actually the implementations we have to be very, I have to say it's quite nice. And obviously, so that is an hard tag question, and there are multiple topics we are. So graph is altogether a very hard topics, and when Leetcode hard questions we are getting on a graph, so that means on like extreme level. So this type of questions you can expect on Google or other companies. I don't say Google Coordination Tower Research. So this type of companies you can expect like that difficulty of the questions. Others, like on others company like Leetcode medium or medium hard, you should be fine. But at least you are able to traverse on a graph. You can think about the DP. So that's the maximum difficulty. But that is a Leetcode hard with graph topic. So that is going to be a super on another boat altogether. So I am before starting the video of the solutions, I am just stating you like what the prerequisite for this. You have to know the disjoint set union DSU. If you don't know, then please please do a comments to this video. You can read it from articles, Geeks or Geeks, or some other YouTube channels also. But if you want that I will make a video of my own template, then please do comments to this video, then I will be happy to do so. But I am not going to incorporate disjoint set unions implementations to this video, so otherwise this is going to be a 2 to 3 hours video for sure. So I am making it quite crisp and simple, so I am just going to use my own DSU template here, but the extra logic we have to think that I am going to explain. So now let's jump on the OneNote that we are usually do. So tell me one things, what happens here, why it is not going? अरे यार ये अटक गया क्या? Okay, अब आ गया. हाँ. So basically what we have to think, so if you can think a very deep, and if you have that eagle eye, then so on this particular question I have to say there is an eagle eye altogether needed. So eagle eye, something like this, you have to be very sharply see the things, what is actually going to help us to minimizing our answer, what is actually going to help us to minimize our answer. So if you are visiting, when the answer is not possible altogether, so let's just keep apart from that particular, which is the very easy part. So what actually brings the answer is altogether not possible. If there is a bidirectional graph is given to you, and if you are standing to a particular particular node, and if you reach to a particular node, then if both are belonging to same component, I am assuming you know what is component in graph, so that's a very childish things. On college we have already did this. So what actually, how you can say, like, if the two vertex belonging to same component or not, if the start vertex and end vertex, like 0 and 3, if 0 and 3 are belonging to same component, so that is one component altogether for this graph. If both are belonging to a same component, then can you say answer is always possible? Can you say answer is always possible? We can, right? Because we have bidirectional edges. So that means starting from just start node, we can traverse in a very messy things, and ultimately we should be able to reach our destination node. That's the for sure, because all are connected, all are in a single component, right? So that is one thing. So when answer is then -1, when it is not possible, when the start node, when the start vertex and the end vertex are belonging to two different components, so in that case our answer is -1. As simple as that. And now when answer is possible, what is the minimum if answer is possible? Now let's go to the OneNote. So we have to minimize the bitwise end, and tell me, like, when the bitwise and is altogether going to be minimized, tell me these things. So if I start writing these things 1 0 1, कुछ lags आ रहा है, excellent performance, मैं इसको restart करता हूँ मेरा डिवाइस को. ACL5R, ओके ठीक है, चलो स्पेस डिस्क स्टार्ट हो जाओ फटाफट. So let's suppose we are arbitrarily taking a number. क्या हो गया? अभी आ रहा है ना, 1 0 0 1 1 0, and that is, let's suppose, number x, and number y, let's suppose 0 1 1 0 0 1 1 0 1 0. So basically what actually bitwise and basically do what? So if you know the bitwise and truth table, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is again 0. So only 1 and 1, if both are 1, then only your bit is going to be set. So here you can see, if at any particular bit, if one of them, if either this or this, either A or either B is not set, right, then your resultant is going to be 0. So now if you are bitwise AND of the two number, then if both are identical, then to what is the number is altogether, the bitwise AND of both are also same, because all have the set bit at the same index, all have the set bits. So if both are same, let's suppose I am writing a number 3 is something like this. So 0 1 2 3, that is for 7 9, 0 1 0 1 2 0 1 2 2 2 4 5 6 7, that is for 7, so both are 7, both are 7. So here you can see bitwise AND. If you do bitwise AND, answer is also 7, answer is also 7 in this case. So because all have the set bits at the exact indexes where actually the bit is needed. Now if any of them, so if you can write a number 1 0 1 0, and if you can write a number 0 1 0 1, so here you can see your bitwise AND. So these bits are altogether going to be unset, because this number is smaller, this number is smaller, this number is smaller. So its highest set bit should start at a very some right of the bigger number. From the bigger number, its first set bit would going to be start from some right portions of the bigger number. So here you can see from this portion is its set bit started. So for very left, so for very left, our answer is already all the bits are unset. All the bits are unset. The reason is because this number has all of its bit to its left is unset. All of the bits to its left is unset. Right. So that is one thing. So now can you tell me like, then the bitwise AND of 2, the bitwise AND of 2 is either to be the smaller one, or can be smaller, more smaller than the smaller one, because these bits are altogether going to be, we are not able to set so. We are altogether not going to be set so. So if the above number has 1 to all the places, that is not going to be affect altogether. So this particular portions, we have the probability to first set our bits, but again like for the bigger number, this bit is unset, this bit is unset, so altogether this index is also coming to be 0. So by mathematical inductions we can easily prove the bitwise AND of 2 number is either going to be the smaller number or lesser than my smaller number, or lesser than is going to be the smaller number. How? If both have the set bits, at the same indexes, if both set bit has same index. If so, then my smaller number set bit is not altogether going to be unset, because on the bigger number also there is a set bit. So this bitwise AND is going to be set. But if that is not the case, then smaller number set bit also going to be unset. So number becomes more smaller. So with this assumption, if this theory is proved for two numbers, we can say this is true for n numbers also. Now that is very intuitive. I think you guys are already getting how it is. So if now you have n numbers, let's suppose if I am write some smaller number 0 1 1 0, like this way, 0 0 1 0 1 1 1 0 0 1 0 0, like this way. Like if you have like this way n numbers. So our ultimate bitwise AND, and we are doing bitwise AND of every of bitwise AND of every of. So now a particular bit is going to be set when all of them has the set bit to a particular index. So this bit is altogether not going to be set. This bit is altogether not going to be set. This bit not. So ultimately the resultant is coming to be 0. Now let's suppose we have 0 0 1 0 0 0 1 1 1 1 1 1 1 1 1 0 0 1 1 0, like this way. Let's suppose you have n numbers. So what is the most smallest? So here you can see this number is the most smallest. So now these bits too we are not altogether going to be set, because we have 0. Here you can see everyone has its set bits. So this bit is altogether not going to be turned off, and other places you can say that it is turned off. So on the above case we see it is more than my smaller. But on this case it is equal to my smaller. How it is equivalent to smaller? Because where the smaller number has its set bits, at which indexes my smaller number has set bits, other number also has set bits to that indexes. So like this way, this particular set bit index is altogether not going to be unset, entire bitwise AND. So that is the trick we have to apply. So now if you have this graph where you have n number of in like there can be n, or there can be like infinite number of edges, you have to take the bitwise AND. You have to take the edges bitwise AND, right? Because they have weight associated. If you have to take the edges bitwise AND, then either to this can be the smaller of all of them, or it can be smaller of the smallest number. That can be also possible, because on this test case we have proved it is going to be turned out to the entirely 0, because some number has its set bits to be unset to the indexes, where the very smaller number has its set bits. Like this way, it is also going to be neutralized that set bit of the smaller number also. So yeah, that is the trick. Now tell me how you can say what is the bitwise AND of a smaller of a graph altogether, smaller of a particular component of a graph together. So if are you guys getting this feeling? So if we are doing bitwise AND, of more numbers, if we are doing bitwise AND of more numbers, so our result is altogether going, the chance of the result is going to be decreased. The result is bound to decrease. Either going to be same or bound to decrease. The theorem we have just proved. Either has the chance to be same, or it can be going to be decreased more, because the property of bitwise AND. But for OR it is not. But for OR, if you are consuming more numbers, the chance of bitwise OR is going to be bigger more. But for bitwise AND, that is one operand for which if you are consuming more numbers with the hope that if I consume more number, I have the liability to grow more, but not, because bitwise AND is going to be take the smaller of all of them, or either can be lower of the very smallest element. So now if I can ask you, what is the challenge then? So if both are belonging, if my start and end are belonging to different components, then we told the answer is altogether not possible. We are returning -1 on that case. But if they are belonging to same component, right, then do you have to explore all the possibility of every time and have to tell me that is the bitwise AND of this particular start and end to this particular component, or it is always be fixed, I think it is always be fixed. Why it is so? Because when I am asking, if there is a very complex graph is given to you, like this way, or it can be more complex, and if I have W1, W2, W3, W4, W5, like this way. So if I have to grow from one path, if I have to go to the other path, you can visit a particular node or particular edges multiple times. So you can do like cycling like this way, any number of cycling, or visiting some extra edges. So if I can iterate you to the test cases, so here you can see, like from 0 to 3, what they are doing, so they are going from 0 to 1, and from 1 to 3 we can directly reach to 3, right? But they are going to 0 to 1 and 1 to 2. So here you can see from 0 to 1 and 1 to 2, and then from 2 to 1 they have come back, and from there they are going to 1 to 3. So basically they did these things. So 7 has more set bits, so they just took the smaller number, to reduce its answer, So how they are reducing? So that's the beauty I have already told you. So if I consume more number, my chance of the resultant bitwise AND, of all of them is going to be chance to be more lesser, because of the future, right? On the visiting, I am going to enter a smaller number more. Then what is the bitwise AND I am carrying? That is altogether either going to be the smaller number which I just encountered, or maybe the smaller of that also, or maybe this. So like this way, the consuming more number, the bitwise AND is altogether, the chance of bitwise AND to become more smaller is more vigorous. So that is the fact. So now if I am asking you, what is the smallest work of any two nodes which are belonging to same component, can you tell me? So yes, so that is obviously, so no matter which of the particular node I am asking which are belonging to same component, if I am ask you from 1 and 3 na, so for 0 and 3 they give the answer to be 1, and if I am asking you for 1 and 3, what you can do, you can go to 1 to 2, then from again you back 1 to 2, then 1 to 0, then 1 to 3 you can go. So like this way you can consuming this one to become your answer more smaller. So what is then the case? So the bitwise AND to all the weight belonging to a particular component. So that's the trick. So the bitwise, so if the two node is belonging to the same component, then the result is always going to be fixed, no matter which of the node I am asking for, because I am doing the bitwise AND of every of them. I will be doing the bitwise AND of every of them, every of the weight belonging to that particular component, because that is the way I have the probability to reduce my answer, to reduce my work value to be more lesser. Yeah, so I think I got you the entire gist of this question. And -1 case I already told, when both are belonging to different component, like the start and the end, the query they have thrown to you, then on that case you can say the, -1. And for all other cases, answer is possible and answer is constant. And what's the constant? What is the bitwise AND of this particular component altogether? What is the bitwise AND of that particular component altogether? So I am iterating to you guys to the code, but that is obviously a master level question. That is obviously a very hard and trivial question. And if you don't know disjoint set, then that is not going to be, you might not get the entire gist of the question. But yeah, like you should know the bitwise disjoint set unit. And if you don't know, and if you want that I will make a video for that on the future, then please do comment it on this video. And if I am get a significant comment of to you guys are basically looking for the DSU video, then I will be happy to make by this weekends or as per my time, but I will be happy to do so. So but please do the comments, otherwise I am like basically taking you guys know this DSU and you are able to consuming this question entirely. So because DSU is a very important question and I am used my own template, and you can take my template, but if you don't understand the template altogether, that is not going to be help you, because so you are just blindly going to be use the template. And here also, like I am not exactly use my template, I have to do the modifications, because every question has its own modifications. Like this way there are versatility of the question you can build. Template is common, but there should be some change in the template so that that particular question specific changes is going to be we adapt to the template. But overall, if you don't understand the template altogether from every line, then you are not able to do the so yeah, so do the comments, please do the comments, then I will be happy to make a video for this separate DSU of my own template. Cool. So as you I know, I am considering you guys are knowing, we basically have to take two array. One is parent array, another one is rank array. That is common, and this bit and is for this particular question. So now it is I guess that is now boiled down to how you guys basically implement the things. So I use DSU because that is going to be fast, because here you can see the time constant is, the graph is altogether 10 to the power 5 kind of thing. So if you can do a BFS complexity, we know of V plus E, we go of V plus E, and V plus E, what is 2 into 10 to the power 5, and the query is altogether 10 to the power 5. So if you guys thinking, so for every query I am doing the bitwise AND of all the entire component to a particular go, then you can going to get a TLE for sure, because 10 to the power 2 into 10 to the power 5 into 10 to the power 5 is 2 into 10 to the power 10, and which is going to give you a TLE for sure. So you have to do a pre-processing, and for pre-processing we are using DSU, disjoint set union, right? So now, so I am not going to explain line by line, but yeah, like just for sake of simplicity I am going to explain. But if you don't know DSU, then you might not going to consume this template altogether. So I definitely need to make a separate video of DSU if you guys want to consume the DSU topic altogether. Cool. So we are going to make everyone parents to themselves only by parent I, and we have considered everyone rank to be 1. And why bit and array I put this value. So here you can see like what is the maximum value of a weight can be. So this can be of 10 to the power 5. So if a particular node, is a dangling node altogether, so on that case, like it is not, it doesn't has any age altogether. So on that case, what is the maximum value we can get? That is the maximum value of binary you can get it in the 10 to the power 5 is 131071. If I am going to add one more, then you can see it is going to be 2 into 10 to the power 5. But if I reduce one, it is going to be 131071, and if I am going to reduce one more, then it is going to be less than 10 to the power 5. So we basically need a value to be set to the bitwise AND of everyone that is just greater than my 10 to the power 5. So this number is 131071, which has all of its bits set and which is just greater than 10 to the power 5. So the number is this. I use a very basic like binary to decimal converter. You can search it on Google and you can get these things. Yeah, now that bit and array I have initialized. Now this is the very standard template of my find parents. So it has the capability of path compression also. I am not going to explain how it is going to work. It is very simple, but yeah, if you don't know, then that is very complex. That's the for sure. And now I am doing standard union. So this specific portion is exactly the template I am following. Just as minor modification for this particular question I have added on the union part that I will going to explain. So if both parents are same, if ultimate parents of U and ultimate parents of V are same, then what we are doing the bitwise AND whatever the ultimate parents of U value is holding, we are doing the bitwise AND with W, because that is the age weight we have to consider. And we did and then return. And if they are not same, if If they are not same, then we have to attach one with another. So we then consider rank array. So which of them has smaller rank, we are going to attach this particular guy with a bigger rank value, that is the standard things we are doing. So if you are able to understand, then very good, and if you are not able to understand, then please do the comments. I will definitely need to make a separate video. Like DSU is altogether need a more than 1 hour if I am going to explain in very deep way. So that is going to be for sure. And so this is the things, and I am just attaching its rank, this smaller rank guys to the bigger rank, and then I am doing the parent. I am assigning the parent of u to parent of v as ultimate parent of v rank is more. So I am updating ultimate parent of u that hey you, now your ultimate parent is parent v, and then I am doing the bitwise and part also the same. Bitwise and of ultimate parent of v, I am attaching the bitwise and of ultimate parent of u, and also what is the age weight of this attaching also, like this particular age weight also I have to consider, and that age weight I have also assigned. And if that is not this case, I have to just do the reverse things. I just did the reverse things, and now I am consuming this age, like I am iterating over the age uvw what is given to you, and I am doing the union of uv and w, as simple as that, as simple. And now when I am going to hit by a query, so query is the uv, like start and end. So I call my find pair functions, which is giving me the ultimate parent of u, and again I call for find pair of v, which is giving me the ultimate parent of v. And if I am checking if ultimate parent of u and ultimate parent of v is same, if both are same, so that means they are belonging to same component. So it is going to be same only if both are belonging to the same component. And if they are not belonging to the same component, I am appending my answer with -1. So that on that case, both are belonging to separate components that we just discussed. And if that is so, then my bitwise array is going to store my bitwise AND of this particular entire component, because we are doing this on the union part. Exactly, right? And if I call my bit and array with the ultimate parent of either u or either v, because both are same, then I am going to the bitwise end of the entire component altogether, and I am attaching to my answer. So yeah, like this is as simple as that. Like you have to be a little bit more intelligent to think of the bitwise, how the bitwise AND is going to be help us. If you are consuming more elements, your bitwise AND is going to be reduced more. So that's the beauty we have applied to this question with the standard DSU template, and we are able to get a successful AC. Yeah, so now let's jump on the time complexity. So on time complexity, I have to say, like, this find parents and this union and find pad, this function is generally taking of big of 4 alpha, that is going to be taking of big of 4 alpha. So it is as simple as like big of constant only. It is as fast as big of constant only, but it is big of 4 alpha. Big of 4 alpha sign to nahi hai. So I am attaching big of $4. So dollar, you can say big of 4 alpha, and it is going to be iterate over the edges, and into how many edges we can have. At the max case, it is of 10 to the power 5. Plus again we are iterating over the query. Again we are going to iterate over the query, and again we are calling find pad. So again we know find pad is going to be taking of big of 4 alpha. So now don't ask me what is 4 alpha, what is actually 4. So there is very mathematical proof is altogether there for how DSU is going to be work on big of 4 alpha. But you can definitely say on an interview big of 4 alpha is as equivalent to constant big of 1, as equivalent to big of 1, but it is more than big of 1 for sure. It is more than big of 1 for sure, but it is a constant time. It is a very constant time. And then we again have a 10 raised to the power 5 this complexity, because query can grow at big as 10 to the power 5. And on space part, I have to say we are using couple nahi, three of pair array, rank array, and bit array. So then on that case we are using big of 3n space, big of 3n space. So yeah, that is the most optimal solutions of this particular question, and that is the most reduced TC, time complexity and space complexity, with this DSU algo I am able to come up with. So if you guys able to understand, so I am definitely have to say that is a master level question, and if you don't know this topic altogether, then you might not get the entire gist of this question. But that is obviously a master level question. There is tricks you have to think, there is a bit masking, there is maths, there is DSU, and within the DSU, my own template is not work. I have to make the modifications. So there are lots of things. So that is obviously I have to say a master level question. If you are solving this particular question, that is more than quite nice question, I have to say. So if you guys able to understand this particular question, and if you like my explanation, so please do subscribe to my channel. So that means actually a lot to me. And also please comments to the descriptions of this particular comment box to this video, so that if I'm not able to trigger, like if you guys following me and if you guys able to understand, and for this particular question I am definitely expecting some comments to you guys. So if you are able to consuming this particular question, or if you need some more explanations like DSU, I am feeling that most of the peoples are not aware. So if you are belonging to this particular batch, so please do the comments. I am most happy to make a separate video for that, sure. So yeah guys, that's it for this particular video. And if you are liking to this particular video, liking to our particular channels, liking to my explanation, please subscribe to my channels, and please turn on the notifications, so that when basically we are going to live with the next video, you are going to get the notifications as early as possible. So yeah, that's it for today. Bye guys, let's meet tomorrow with another beautiful question. Bye.